Hello, today I will begin to talk about the dramatic history of so-called quantum wave packets, which started to unfold 100 years ago, but has not yet ended, even in our time. Of course, as soon as Erwin Schrödinger invented his famous equation in 1926, he immediately verified that free particles as material mass points move faster than the corresponding quantum waves obtained from his equation. As we have seen in the previous story, the speed of free particles is twice as large as the speed of corresponding quantum waves. The newly created quantum theory could not exist without an explanation of this paradox. However, this fact did not turn out to be an unpleasant, unexpected surprise for Schrödinger. 2 years earlier, in 1924, Louis de Broglie had already described this problem in his glorious PhD thesis and proposed a way how to mitigate this challenge using the concept of groups of waves. Referring to the authority of Louis de Broglie, Schrödinger pointed out already in the second scientific publication devoted to his equation that moving material points can be represented by groups of waves with close frequencies. Today, such groups of waves are better known as wave packets. Now we will discuss how it works. Many of you have probably noticed the visual illusion of the movement of running patterns on board fences if you walk along to such fences and look at them. These moving visual clusters or patterns on fences are the simplest natural examples of wave packets. We can also demonstrate the illusion of both stationary and traveling wave packets using two hair combs with slightly different tooth spacings. If I adjust properly positions of motionless combs, then we will see motionless patterns. Then I begin to move the first comb to the right at low speed. We see that the patterns begin to move to the right at a much faster rate. Surprisingly, if I stop the first comb and start to move the second one to the right, the patterns now move to the left. Thus, we see that depending on the distances between the similar recurring elements of periodic structures such as our combs and the relative velocities of the structures, we can observe a wide variety of created standing and traveling wave packets. We will now derive formulas for the packet speed, but first we will make an important note and change in the formulation of the problem. When overlapping the teeth of two combs, their heights do not add up and do not stack one on top of the other. That is why the visual center of the running duck pattern for two combs is located where the teeth of one comb fall into the gap between the teeth of the other comb. In other words, in our example with combs, we see the centers of the packets in those places where the tops or crests of the waves fall on the troughs. In contrast, the local heights of water waves, quantum waves, and other similar waves add up. We can easily demonstrate such a simple packet if we just superpose the values of two cosine waves traveling together. If two crests coincide in space, then they are added one above the other, and the height of the resulting wave is twice as high in this place compared to the height of each individual crest. Therefore, the centers of quantum wave packets are located where crests meet crests. For further analysis, we will artificially split two waves up and down along the vertical axis. Moreover, for visual clarity, I will add one more wave, and thus we will be looking at the interference of three moving waves. For each of the three waves, we will only monitor the movement of the two maximums, which we will also call the left and right crest or humps or heights. At zero time, all left crests are aligned in one line, but right ones are disaligned. As time increases, all three waves fly to the right. After some time, the right hump of the second wave catches up with the same hump of the first wave. Just like in the de Broglie wave in our example, the angular frequency omega is proportional to the square of the wave number k. It turns out that with this relationship between frequencies and wave numbers, the third wave will catch up and even slightly outrun the first wave at the same moment in time when the second wave catches up with the first one, as we see in our demonstration. For now, we will ignore this outrun effect and assume that all three waves met together at one point in time. Thus, we see that the center of the packet of 2, 3, or any other number of interfering traveling waves of the de Broglie type will move over some time to the area where the right maxima are located. The wave packet moves at a speed exceeding the speeds of the individual waves that make up the packet. Now we will repeat our animation and mark the starting and ending positions for only two waves out of three ones. After scratching all the wavy curves, we can see a relatively simple scheme presented here. We will write all parameters of the first wave with our subindexes as wave number k, frequency omega, wavelength lambda, and phase velocity u. On the contrary, all parameters of the second wave will be marked with the subindex 1. Initial distance between right heights is equal to delta lambda, which is equal to the difference between wavelengths of two waves. Let's denote the time of alignment of the right maximum as ta. Within this time interval, the center of the pocket will cover the distance L plus lambda, that is, its speed will be L plus lambda over ta. Moving at speed u after time ta, the right crest of the first wave will cover some distance L. The right hump of the second wave will cover the distance L plus delta lambda at speed u sub 1 within the same time. After not too complex but slightly cumbersome transformations, we can obtain a simple relation that the group velocity is equal to the ratio of delta omega over delta k. We can obtain the same expression in a simpler way for the sum of two traveling cosine waves. Using the formula for the sum of cosines, we see that the resulting pocket is formed by a moving envelope that modulates the carrier wave. The pocket speed is equal to the envelope speed, which is equal to delta omega over delta k. Now we know the relation for the group velocity for a pocket of two waves, and we need to generalize this result for the case of three or more waves in the pocket. We have just seen that in a general case the maxima of even three waves do not gather strictly simultaneously at the point of the new position of the center of the pocket. Therefore, both the position of the pocket and its speed can be determined only approximately. We should do this in the most sensible way. A small segment on the graph of any function including omega versus k can be represented as a straight line. For any 2 points on this line, the ratio of delta omega to delta k is the same. In order to obtain the same straight line and the same ratio of delta omega to delta k for the same starting point on the curve chosen by us in different measurements, we must direct delta k to 0 to ensure reproducibility of the results. Thus, the group velocity of a pocket is defined as the limit of the ratio of delta omega to delta k under the condition that delta k tends to 0. By definition, such limit is called the derivative of omega with respect to k. This formula is widely known in physics. The greater the deviations of the frequencies of the elementary waves that make up the pocket from the straight line, the more unevenly the various parts of the envelope of the pocket move, and the more the pocket deforms during movement. Now let's consider the Broglie waves for free atomic particles. From previous stories, we know that in this case the frequency is related to the wave number by the relation omega is h bar squared over 2m. Having performed the transformations and remembering that the velocity v of a free particle is equal to h bar k over m, we obtain that the group velocity of a pocket of two waves is equal to v plus h bar delta k over 2m. The remarkable fact that the shape of the envelope of a pocket of two de Broglie waves remains unchanged as the pocket moves. This follows from the formula for the sum of two cosines that we have discussed a little earlier. The group velocity of a pocket of three or more de Broglie waves is exactly equal to the classical velocity of the particle. This is an encouraging result which both de Broglie and Schrödinger hoped to use in their theories, despite the fact that each individual de Broglie wave moves at half the speed v of the relevant atomic particle. We can assemble a group of these waves that will move at speed v. However, the shape of the pocket of three or more de Broglie waves doesn't remain unchanged over time. As we just noted, the linear component of the function omega of k ensures the movement of the pocket at speed v as a whole individual system, but non-linear additives can lead to deformation of the pocket during its movement. Our next task on the agenda is to evaluate the impact of these nonlinear variances. In order to understand this issue, let's consider as an example a fully fledged pocket composed of a large number of de Broglie waves, and compare its time behavior with almost the same approximating pocket with discarded nonlinear additions. As we have already discussed in my last stories, in general case, we need to take a pocket made up of complex exponential functions representing elementary de Broglie waves. Using earliest formulas, this sum can be rewritten as the sum of cosines and sines. The sum of sines must be labeled with an imaginary unit as a multiplier. The wave numbers k sub j of elementary waves differ by a constant step delta k. Angular frequencies omega j depend on wave numbers by quadratic relations common for de Broglie waves. Next, we will use the so-called atomic units for time, length, and mass, and also assume that our particle is an electron. In this case, we can formally apply that both h bar and mass are equal to unity, and thus omega sub j is equal to half of k sub j squared. In further visual demonstrations, we will use a packet consisting of 21 waves with the numerical parameters specified in this figure. For simplicity, we will consider only the real component of the wave packet, represented by the sum of cosines. So you can reproduce all the results yourself using Excel or Python or any other suitable program. In order to create the desired approximating packet, we must expand the square brackets in the formula for frequency and then discard the last small term. As a result, we obtain a function a of x and t, which consists of the sum of cosines with coefficients that are very close to the coefficients in the formula for the exact de Broglie packet psi1 of x and t. Unfortunately, the original packet psi1 of xt doesn't allow conversion to a short formula for arbitrary x and t. In contrast, function a of xt can be converted into a short formula and represented as a rapidly oscillating function modulated by an envelope, as we have discussed in my story number 6 earlier. You should not be afraid of the fact that the sign in the denominator can turn into zero. The formula is designed in such a way that in these cases the numerator also goes to zero, and as a result we get a limited value. It is well known that the sign of an angle is approximately equal to the angle itself if the angle is small. This follows from the linearity of the sine graph near zero. You can also check this rule yourself using any online calculator. Thus, we can get that the ratio of the sines tends to 2n plus 1 if the phase delta kx minus delta omega t tends to 0. Our simplified packet A of xt demonstrates excellent properties. It can be represented either by a long sum of cosines or by a short but highly informative formula with a Kähler wave and the envelope. Its group velocity is equal to the classical velocity of the particle. The shape of the packet remains the same as the packet moves. But unfortunately, it has one very serious defect. It doesn't satisfy the Schrödinger equation because we constructed this beautiful packet using corrupted de Broglie waves with dropped quadratic terms. In contrast to this, the initial packet psi1 consists of a sum of elementary de Broglie waves. Each elementary wave satisfies the Schrödinger equation. Therefore, psi1 packet also satisfies this equation. Now we need to superimpose one packet on another and visually compare their time evolution. But we will do this in the next story. Please do not hesitate to leave your comments under this video if you found this story helpful or if you noticed any mistakes. Your comments are very important to improve the quality of these materials. Thank you for attention.